Hello friends, welcome to Wisdom Jobs. In this video, I am going to explain you about the last rule which is to be followed for determining the electronic configuration of a given element. The last rule is Hund's rule of maximum multiplicity. Before going to explain this rule, I request all of you to subscribe to our channel Wisdom Jobs at the earliest so that you are not going to miss the different classes which are important in the exam point of view. So if you have got any doubts in this class, please do express them in the form of comments or suggestions in the comment box. So your doubts and all the all of your queries would be answered time to time whenever we find some free time. Okay, let me get into the class. Now in the previous videos I have explained you two different rules, that is Pauli's exclusion principle and, if you remember, Aufbau's rule. So one more is N plus L rule. So N plus L rule talks about the energy of a particular shell and subshell, and Pauli's exclusion principle says that no two electrons have got the same electronic configuration. I mean, no two electrons have got the same set of the quantum numbers. Like if they are same, if they are having same quantum numbers of principal quantum number, azimuthal quantum number and magnetic quantum number, at least they are going to differ in the spin quantum number. That's what is Pauli's exclusion principle. Now let me explain you the last rule which is to be followed while writing the electronic configuration of a given element. The last rule is Hund's rule of maximum multiplicity. Now in this rule he says that the electron pairing will be taking place only when each orbital have got at least one electron. Now I already told you what is an orbital in the last video, but I am going to reiterate it once again. Now the areas around the nucleus in an atom where the probability of finding an electron is maximum, those regions around the nucleus in an atom are called orbitals. Now in each orbital it can accommodate two electrons, so one with a positive spin or anti-clockwise direction and one with a negative spin or clockwise direction. So Hund's rule of maximum multiplicity says that in any degenerate orbitals, what are degenerate orbitals? The orbitals in the same shell are called degenerate orbitals. So in the Hund's rule says that the electron pairing in p, d and f orbitals cannot occur until each orbital of a given subshell contains one electron each. That means for example, if I take 2p orbital, so what are the orbitals we have in 2p? 2px, 2py and 2pz. And in this 2p orbitals, for example, if I am to fill 4 electrons, so if I am to fill 4 electrons, then the pairing will not be like this. So here, first of all, every orbital will get 1. And how many are already over? 1 here in 2px, 1 here in 2py and 1 in 2pz. So already 3 electrons are over. So now comes the pairing. So since there are 4 electrons, the 4th electron is to be filled in one of the orbitals and that is filled here. So in toto, the effective electronic configuration would be becoming 2px 2, 2py 1 and 2pz1. Okay, so this is the correct way of determining filling the electronic configuration in 2p subshell. Now what is the wrong way, or which is incorrect way of writing the electronic configuration is, since I am having 4 electrons, I cannot write 2p x2 and 2p y2, okay, and 2p z0. So what is it that you are going to observe in the second configuration? In this configuration, here we are first filling what? 2px2 and 2py2, and since there are only 4 electrons, no electron is filled in 2pz. This is wrong concept. This is what is told by Hund's rule. So Hund's rule states that the pairing of electrons will take place only after every degenerate orbital is being filled. Now I'll give you one more example so that you don't have any confusion. Now if I give you one more example, like, or let me say that of 3D orbitals. So if I am having in the 3D orbital, if I should fill, let me say 7 electrons. So how many d orbitals are possible? The d orbitals for possible are 5 in number. Why? Because it is the d orbitals can be d x square, dy square, dz square, dx square minus y square, and dz square. Okay, so I'll write the orbital names. So it is, first of all, 3d x square, 3d y square, 3d z square, 3d x square minus y square, and 3d z square. Okay, now I am supposed to fill total of 7 electrons, right? So if I am supposed to fill total of 7 electrons by a layman rule, if I am a layman not knowing Hund's rule, then what will I do? I will directly go with 2, 2, 2 and 1. So how many are there? 2 here, 2 here, 2 here. So 6 plus 1, 7, and I will put a 0 here. So this method of filling is wrong. Now Hund's rule says that pairing should be done after every degenerate orbital is having at least 1 electron. So that means how to apply Hund's rule here? For the same example, it is 3d x square, and first let us write every orbital has got 1 electron. So 3d y square 1, next 3d z square 1, and 3d x square minus y square, here also 1, and 3d z square, here also 1. Okay, now after each orbital has got 1 electron at least, okay, now we are going to pair. So after every orbital got 5 electrons, how many are remaining in the 7 electrons? See, since there are 5 already filled, so 2 electrons are remaining. So in these 2 electrons, I'll give the 3d x square orbital 1, 3d y square orbital 1. Okay, so actually this is xy, yz and zx. So I'm sorry, and lastly x square minus y square and z square. Okay, so here also it is xy, yz and zx. Now here, after every orbital got 1 each, then I am going to pair, and effectively it is what? 3d xy 2, 1 plus 1, next 3d yz 2, which is 1 plus 1, and 3d zx 1, because there is no pairing here. Similarly 3d x square minus y square, and finally 1 here, and 3d z square, here also it is 1. Okay, now this is how we are going to write the electronic configuration after following the Hund's rule. Now what is the basis for Hund's rule, and why should I think that this Hund's rule is correct? Is, now if at all I am having 2 electrons in each orbital. So for example, without following the Hund's rule, let me explain you this format only. So in the first format, which is incorrect, what is going to happen? 3d xy orbital has got 2 electrons. Okay, and if I am having 2 electrons in one space, as per the principle like dislikes like, or like repels like. So we have got one principle called like charges repel. Okay, so if on a jokey note, if you observe, the attraction between a boy and a girl is more when compared to the attraction between a boy and a boy. That's a nature actually, is it not? So in the same way, electrons are 2 likely charged particles, so they don't try to exist in a common place. So obviously they try to repel each other, and that might create escaping of electrons from the orbital. So in order not to escape, we need to first pair the electrons with each one. So if I am considering orbital as a room, in one room better you have 1 electron than 2 electrons. Yeah, when one is already filled, and if there is a chance of filling the second, yeah, then there is no chance, and obviously the second electron will be coming and sitting in the same orbital. So pairing will minimize the repulsions. So electron repulsions are minimized by Hund's rule, and that's the reason why we pair the electrons first, at least after every orbital has got one electron, and then pairing is going to be started. Okay, in this way I can apply the Hund's rule. Next, let me explain you the electronic configuration in terms of ions. Okay, now before going to ions, I should explain you what is ground state and what is excited state. Now, what is ground state? Any person, for that matter, any person, if he is dull or if he is normal, he is in the normal state. Okay, and when he gets a lottery, or when he got to know some exciting news, obviously what is going to happen? He gets excited. That means there is an external energy which is driving him so that he gets excited. So in excitation state of a person, he has got a higher level of energy, and in his normal level, he has got a low level of energy. So the low level of energy or normal energy state in a person is analogous to ground state. So now if you take an electron which is not supplied with any energy, then it is said to be in its ground state. So what is ground state of an electron? The state of an electron without any application of external energy. Such state of an electron we are going to call it as ground state. So in ground state there are no violations required. So we follow all the rules like N+L rule, Pauli's exclusion principle, next comes Afuba's principle, and finally Hund's rule. So all these principles we follow for writing the electronic configuration of an electron in ground state of any given element. Now what is an ion? Next question is, what is an ion? So as I just now told you, what is excitation? Supplying of energy makes an electron get excited. So here also, if an atom is been given an external energy supplied to it, so it gets excited, and that in that excitation state, what's going to happen? The outermost electrons, either they lose their path and the valence electrons will be going away, or one more possibility is that external positive charges can be coming and attaching to it, positive or of course negative. So if a metal is losing electrons, okay, let me say it loses one electron. So if I am saying that a metal is losing one electron, how many electronic charges would be there, or how many negative charges would be there? One less than the positive charges in the nucleus. So I'll try to explain you once again. Here we have got, let me say, let us take sodium atom. In sodium atom we have got 11 protons and 11 electrons. Out of 11 electrons, if one is going away, so how many protons will be there? In the proton number there won't be any change, because the losing element is electron. So 11 protons will be as it is there in the nucleus of the sodium, and out of 11 electrons outside the nucleus, one electron is going away as valency electron. So obviously what is going to happen? The number of electrons in sodium after excitation reduces to 10 electrons. So 11 protons and 10 electrons make sodium a positive ion because the number of protons are more in number. So here this is going to become M+. So we put as many number of plus signs here as it loses the number of electrons. For example, if it is losing 2 electrons, so if the metal atom is losing 2 electrons, then it is going to become M2 plus or M++. Okay, now if it is, let me say, getting reduced by 3 electrons, or it is losing 3 electrons, just like in the case of aluminium or gallium, so it is going to become M3+. So the number of positive signs is equal to the number of electrons that are lost by that particular element. So this is said to be an ion. Okay, and ion is unstable in its existence, and it tries to get once again stability by either discharging this positive charge. Okay, so now let me explain you how to write the electronic configuration of an ion. Now if you take that of a ion, just reduce the number of charges in its outermost orbit, and for that number of electrons you write the electronic configuration. That would be your electronic configuration of that particular ion. Now let me give you an example. So if I take the example of sodium ion, or let me say magnesium. So magnesium ion would be stable in 2+ state. Why it is stable in 2+ state? Because its outermost orbit contains 2 electrons. So if I take Mg2+, how many electrons are there here? 10 electrons are there. So in Mg2+, we have got 12 minus 2, which is 10 electrons. So now the electronic configuration would be 1s, 2s, 2p. Okay. Now for 10 electrons, here 1s contains 2 electrons, 2s contains 2 electrons, and p shell contains how many electrons? It contains a maximum of 6 electrons. So 2p is 6. So already if you take 2 plus 2 plus 6 will give you 10. So all the 10 electrons are already completely filled. So for the magnesium atom, the electronic configuration is, for the magnesium ion, this is the electronic configuration. So what did I do here? How did I write this electronic configuration? Based on the number of electrons in the given ion, I am going to write the electronic configuration, but we don't take into consideration the original atomic number of magnesium. Understood? So in this way I am going to write the electronic configuration of any given element, any given ion. Now let me comment on the magnetic moment. Okay, so if the number of unpaired electrons are n in a particular element, let us say in chlorine. So in chlorine, how many unpaired electrons will be there? The atomic number of chlorine is 17. So if you observe 17, it contains one unpaired electron. That means it is if I write 3p subshells electronic configuration, it is 3px2, 3py2, and 3pz2. Sorry, 3py2 and 3pz1. Okay, so obviously how many unpaired electrons are there? Only one unpaired electron. So for the case of chlorine, n is equals to 1. Okay, so obviously what would be the magnetic moment for sodium? It is mu is equals to, the basic formula is what? Mu is equals to under root of n into n plus 2, where n into n plus 2, where n is the total number of unpaired electrons. So substitute n equal to 1 here. So what do we get? It is equals to under root of 1 into 1 plus 2, that is root 3. So obviously mu is equals to root 3 for the case of chlorine. Okay, now let me take in the excited state that of magnesium. So magnesium has got 2 electrons in its outermost orbit, and in the excited state, 1 electron from 3s subshell will be moving to 3p subshell. So in the excited state of magnesium, we have got 2 unpaired electrons. So obviously for the magnesium atom in excited state, what would be the magnetic moment? Let me calculate the magnetic moment for magnesium in excited state. So since n is equals to 2 for excited magnesium, obviously the magnetic moment mu is equals to under root of 2 into 2 plus 2. Or simply it is 2 into 4 under root, which is root 8. So in this way I can calculate the magnetic moment of any given element, provided you know the number of unpaired electrons in the given atom or in the given element. Okay, now with this we have sufficiently covered what is the topic of electronic configurations and what are the different rules that are to be followed while writing the electronic configuration of a given element. So if you have got any queries on this topic, please do express your doubts or queries at the end of your session in the comment box provided. As and when we see your queries, we are going to answer your queries and try to clarify your doubts. So please do subscribe to our channel and please tune to our channel for regular updates, because for your helping, we are uploading all the data and important videos and important concepts on a day-to-day basis. So if you are not subscribing, you are going to miss many videos, my dear. So please do subscribe to our channel Wisdom Jobs. Thank you for watching this video.